So let's say we have state 1 and we have state 2. So there's heat transfer here and there is work done. So we have the internal energy, like this one is E2 and this one is E1. So the point is, any thermodynamic system in an equilibrium state possesses a state variable called internal energy, right? Between any two equilibrium states, the change in internal energy is equal to the difference of heat transfer, this one, into the system and work done by the system. Heat transfer into the system and work done by the system. So we call this thing first laws of thermodynamics. So here we have some process terminologies. The first one is adiabatic and isothermal, isobaric and isochloric. Adiabatic means no heat transfer. There's isothermal is constant temperature, isobaric means constant pressure, and isochloric means constant volume. So let's see about adiabatic process. An adiabatic process transfers no heat, therefore Q is 0. So we have this one, right? This one is 0. So we have the change in internal energy is equal to negative W, work done. So what does this mean? When a system expands adiabatically, W is positive. We take this one positive, right? So the system does work. So this one is what? Negative. But when the system compresses adiabatically, W is negative. So when we make it negative, internal energy is equal to negative of negative. We get what? Positive. So internal energy is positive. This is the concept of adiabatic process. Isothermal process is like, an isothermal process is a constant temperature process. Any heat flow into or out of system must be slow enough to maintain thermal equilibrium, right? So for ideal gas, if change in temperature is 0, so also obvious there is no internal energy is 0, so therefore Q is equal to W. What does it mean? Any energy entering the system must leave as work W. This is like for ideal gas. This works for ideal gas. Which one is isothermal process? And the third one is isobaric process. An isobaric process is a constant pressure process. We have internal energy, we have work done by the system, and we have heat added to the system are general non-zero. But calculating the work done by ideal gas is straightforward. But in isobaric, we have constant pressure, so if we need to calculate work done, work is equal to P times change in V. This is simple for isobaric process. We have then isochloric process, which is isochloric process, constant volume process. When the volume of system doesn't change, it will do no work on its surrounding. So we were saying like this, right? Work is equal to P times change in volume. But this one, change in volume, means we have volume final minus volume initial. If there is no change in volume, this one will be 0, so work is 0, work done. So we have change U is equal to with the heat. So we call this one isochloric process, which is constant volume. The other term that I want to see, heat capacity. What does mean heat capacity? When we say heat capacity, the amount of heat required to raise a certain mass of a material by a certain temperature is called heat capacity. The amount of heat required to raise a certain mass of a material by a certain temperature is called heat capacity. This is an amazing concept actually. So we can calculate this. mCx change in T. This one's mass, this one change in temperature. This Cx means specific heat of a substance, and its SI unit is J in joule per kilogram per Kelvin. Okay, so this one equals specific heat of a substance, which is the amount of heat required to raise a certain mass of a material by a certain temperature. I want you to bear this thing in your mind. Let's take like as an introduction, heat capacity of an ideal gas. So we have Cv, heat capacity at constant volume, we have this one. Cp, heat capacity at constant pressure, we have this one. For constant volume, we have Q, this one. So like this one is, I think, universal gas constant, and its value is this one, 8.314 joule per mole per Kelvin. Okay, so now let's see, you can break even. The second law of thermodynamics. Think about what it means to not break even. Every effort you put forth, no matter how efficient you are, you will have a tiny bit of waste. So you couldn't convert every input into an energy. There is waste. So that's why we are saying you can't break even. This one is second law of thermodynamics. And the second law can also be said that heat flows spontaneously from a hot object to a cold object. Spontaneously means without the resistance of external work, but there is still waste. Okay, so we have a tiny bit of waste.